Okay, hello students, and welcome to today's lesson. We're looking at scientific notation. So the point of today's lesson is that you'll be able to write numbers in scientific notation using significant figures. To start off, we're going to have a look at something called the scale of the universe. And what this does is just helps us to get a picture of how big things are and why we might want to use scientific notation. So if I have a look at this, everything here, this circle represents 1 metre. So you can see a person is approximately 2 metres. A dodo bird, well, that was what, about 1 metre in height. Beach ball, well, that's about 80 centimetres. Now I'm going to just take a note of this. So this is scrolling in, so you can see that things are getting smaller and smaller. So sleet, for example, is a bit of ice from the sky. How big is an ant? An ant is about 4 millimetres. So that looks like saying 10 to the negative 2 or negative 3. So it's pretty small there. Now 10 to the negative 3 is also just like saying 0.001 metres. So remember that 10 to the negative 3 is like 1 over 10 to the third or 1 over 1,000. So 1 millimetre is like saying 10 to the negative 3. So our largest bacteria are about 1 mil in size, or about actually 1/3 of a mil. Grain of salt, you can still fit a few grains of salt in a millimetre. Let's go even further. The width of a human hair, let's click on that. So that's about 100 micrometres, which is about 1/10 of a millimetre. Now a micrometre is 1/1000th of a metre. So we are getting really small. So let's have a look. Clay particle. What else? Our largest virus is what? 10 to the negative 1, 2, 3, 4, 5, 6. So we said 10 to the negative 6 metres. So that's pretty small, isn't it? So let's keep going. Hepatitis B virus, DNA. That's the layer, the phospholipid bilayer is the outside of your cell. What else is interesting? Okay, our atoms. Our carbon atom here is, well, let's have a look. It's 340 picometers. Well, what's that? Like 10 to the negative 12 for a picometer. So it's like lots of decimal points in lots of zeros after the decimal point. Is here 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is around 10 to the negative 9, this circle at the moment. You can see this carbon atom is a bit smaller than that, so that's probably 10 to the negative 10 or thereabouts. Let's keep going smaller. Hydrogen atom, that's our smallest known atoms there. Yeah, they are often called our angstroms. Can I click on that? So this is the size of an angstrom is usually occasionally use that for the size of atoms. We don't often talk about that at school though. Now picometer I mentioned before, 10 to the negative 12. And now we're starting to look at the nuclei of atoms. You know, you often thought that electrons were about that, and they're probably even a bit smaller than that. So now we're not really sure about things that are smaller than 10 to the negative 16. That's lots of zeros, but they're hypothesized. So let's have a look. So quarks, so up quarks and down quarks, etc. make up atoms. Neutrinos, so we can keep going smaller and smaller. And let's zoom back out now. And let's see if we can go back to 1 metre. So that's like 10 to the power of 1. So yeah, here we are. So sunflowers sometimes go taller than humans. Yep, that's right. Elephants. How big are elephants? Well, they're about 5 metres. So 5 times 10 to the power of 0 in this case. Look, a Boeing 747 with 65 metres. So now let's have a look. We've got 10 to the power of 3 here. So 10 to the power of 3 is what? 10, so it's got 1 with 3 zeros after it. Uluru, we know there's rock, don't we? So what else? What's this? This is Earth's second moon. Well, there you go. I didn't know about that. It just follows around the sun near us. Oh, okay, so it's a bunch of rock that sort of acts like our moon. Let's have a look what's big. Okay, that looks like a moon or some planet. What's that? West Virginia. Here's our Grand Canyon. Rwanda. Oh, here's Italy. Now we're starting to get into our planets, or our moons, I should say. Well, Pluto's no longer a planet. It used to be a moon of Neptune. You can start to see, well, okay, here's Earth. You can see here are the moons. What's our Minecraft world? I suppose that's pretty important to a few of us. Planets are our gas giants, for example. And this is a planet out there somewhere. Now we're starting to get into our stars. So here's our sun. So it's what, 1,400,000 kilometres, or 1.4 times 10 to the power of 9. So we're dealing with some really large numbers here. So nebula, and so you can see things are just getting crazy, but I better get on to today's lesson, hey. So the main point of today's lesson is, why do we use scientific notation? Well, you can see there that we're just dealing with some really large numbers or some really small numbers, and so it's easier to use something called scientific notation. So let's have a look at our key ideas. So a number is written in scientific notation if it's a product of the number between 1 and 10 and a power of 10. So it might be, for example, a times 10 to the power of m, where a is, what's this? It's greater than 1, greater than or equal to 1, but it's smaller than 10. So it's between 1 and 10, and m is an integer, so that's a whole number. So if m is a positive integer, then the number is larger than or equal to 10. If it's a negative integer, then the number is between 0 and 1. So a shortcut can be used to change a number in scientific notation to a basic numeral. The power indicates the number of places a decimal point is moved. So if the power is positive, move the decimal point to the right. If the power is negative, move the decimal point to the left. That's a nice, easy shortcut there. To write a number in scientific notation, place the decimal point after the first non-zero digit and multiply it by appropriate power of 10. So for example, 31,500 becomes 3.15 times 10 to the power of 4. I'm just going 1, 2, 3, 4. So that's how I get that. Or 0.42 becomes 4.22 times 10 to the power of 1, negative 2, because I'm moving right. Now, the number of significant figures is a measurement that indicates the level of accuracy. Okay, and all digits in numbers written in scientific form are significant. So let's have a look at our first one. We've got 7.2 times 10 to the negative, times 10 to the 6. So, well, it's going to have 7, 2, and then I'm going to have to go 1, 2, 3, 4, 5. So let's have a look at that. 1, 2, 3, 4, 5, 6. Yeah, so that's 7,200,000. And there's 6 decimal places in that. Now let's have a look at 3.4 times 10 to the negative 8. Well, I'm going to have to put a bunch of zeros in front of that. So let's have a look. I'm going to have to go 1, 2, 3, 4, 5, 6, 7, and now I put my 3.4. Excuse my messy writing, it's a bit hard on the screen here. Okay, now let's have a look at writing each of these in scientific notation. Now it's going to be, start off with 2.3. So I've got my first non-zero digit, which is a 2. And then I'm going to place a decimal point after that 2. So it's got to, remember, this number has got to be between 1 and 10. So greater than 1 and less than 10. So this is a 2. Then we put the decimal place. Now we just count the number of points. So 1, 2, 3, 4, 5. So it's 2.3 times 10 to the power of 5. Now let's have a look at this next one. It's got to be 8.56 times 10 to the power of negative something. Let's work it out. -1, -2, -3, -4. So it's 8.56 times 10 to the -4. Let's have a look at significant figures. Now, a significant figure is important when you want to be accurate. So if I have a look at this one, I've got all of these are non-zero digits. So I've got 3 significant figures. So I just write 3SF. If you do senior science, you'll do a lot of this. The next one is all these placeholder zeros between those non-zero digits are significant. So in this case, we've got 5 significant figures. Now, zeros at the end of a decimal number are significant. So let's have a look at this. So if I'm going 6.200 meters, let's just think about this. That's also like saying, what? I could say it's 62.00 centimeters or 620 millimeters. Is that right? I think I've out by a factor of 100, out by a factor of 10. So let's do that again. So there's 100 centimeters to the meter. So it's 620 centimeters or 6,200 millimeters. So we can say that that's accurate to the nearest millimeter. If I just said 6.2 meters, it's not as accurate or precise. Okay. Now the next one is a tricky one. So this one here. So we've got these 3 zeros. So the zeros at the end of an integer are not significant. So these ones come after the decimal point, but we don't know how precise we are there. So this one, 6.200 has 4 significant figures, but this one only has 1 significant figure. I suspect this is what a few of you might be confused on. And then if we have a look next here, similar sort of issue, these are not significant and these are not significant. So we've only got 2 sig figs there. And the reason for that is that zeros to the left of the first non-zero digit and a decimal number are not significant. Okay, let's write each number in scientific notation with the number of sig figs indicated in brackets. So we want 2 sig figs, so it's going to be 5.4 something, isn't it? So I have to round that up. That rounds up to 54,000, but we only want 2 sig figs. And I could write them in scientific notation as well. So that's times 10 to 1, 2, 3, 4, times 10 to the power of 4 as well. Now I see we just want, in this case, it's the same as rounding off to 54,000. Okay, let's have a look at this one. We have a look at the next here. I actually want 3 sig figs for this one. So we are just looking at these 3 here. So it's just going to be 0.0840. Oh, that's a bit weird. Oh yeah, I see we did that there. And then we can just express it as scientific notation. So it's just going to be 8.4 times 10 to the -2 because I moved that decimal place twice. Okay, copy down those notes and then just my scratchings there. And have a go at the mastery questions, please, students.